Hi, and welcome to another geometry gem. In this one, what we're going to do is we're going to find a point along a line, or a point in between two other points. We're going to do it in two different ways. One is going to be by using normalized coordinates or using relative coordinates. So, for example, this point that you see here, no matter how much we move the line or what it is, it's always going to be at the center of the line. And if we do 0, it's going to be at the beginning, and if we do 1, it's always going to be at the end. Those are relative coordinates, but also we're going to implement like a slight variation of that, where the units are going to be, instead of relative to the length of the line, are going to be in Euclidean values, or basically in world units. So if this is 5 units, 3 units, so the point is always going to stay at that fixed length along that line. All right. I'm going to be using Rhino and Grasshopper, which is an algorithmic modeling environment, just for the sake of having easy visualization of this algorithm. But the code is going to be written in native C# without any libraries. So if you will see that what you will learn from this gem will be very easy to translate to any other of your favorite programming languages. All right. So let's get to this. All right, let's get started. So I'm going to explain first how the algorithm works. And it's going to be super simple because it's also one of the most foundational geometry algorithms that you can think of. And I'm going to explain it in two ways. I'm going to explain it like geometrically or numerically. I don't know what that one is, but I'm also going to explain it from a vector algebra interpretation. So whichever one resonates with you better, that's probably the interpretation that you want from this algorithm. So remember, what we're calculating is a point at a relative distance along a line. But as usual, a line is not a line. What a line is, in fact, is just a line is defined by the 2 points at the ends of that line segment. Okay, we're always going to work with line segments. Lines, by definition, are actually infinite. So a line segment is a much more appropriate way of talking about something that has a start and an end linearly. So for us, what's important is the 2 points. And what we want is to find a point somewhere in the middle of those 2 points at a distance along that line that is relative to a factor. We're going to call that factor n. And it's going to be relative because when this factor is 0, c is going to be basically at the starting point of the line. When that factor is 1, the point c is going to be at the end of the line, so it's going to be b. And when it has any other value between 0 and 1, it's going to be in the range between these 2 points. No matter how long this line is actually in Euclidean terms, what we want is the relative distance along this one. So if we know that, we will know that if n is 0.5, then c will be in the actual middle, in the actual center of this line. But how do we calculate that? Well, it's actually quite easy, because if we know that this line in space, and I'm talking 2D here, but everything applies to 3D as well. If we know that this line, the distance between the 2 points has an x component, so we can find from the coordinates of b and a, we can find how far apart in the x direction they are, and how far apart in the y direction they are, then it follows geometrically that how far away c is going to be from the first point in the x direction and in the y direction is also exactly proportional to how far away it is along the actual line. So if this is 0.5, this point is going to be along x is going to be 0.5 times the distance in the x direction between a and b. And if this point is 0.5 on the y direction, is also going to be 0.5 times the difference in the y direction between these 2 points. So the algorithm will be as simple as computing the distance between the 2 points in x, y, and z, and then multiplying those distances by the factor, the relative factor that we are inputting, and then with those values, creating this point by taking the initial point and adding those values x, y, and z to that point. So that's the geometry or numerical interpretation of the algorithm. If you are more of a vector algebra person, you can look at this problem from a different perspective. You can look at this problem as saying we have the line, we have the two endpoints, and we know that these 2 points form a vector between them. This vector, if we call this vector AB, then we know that this vector is defined by subtracting from the coordinates of B, subtracting the coordinates of A. This is how we can calculate this vector. And we know that if we want to find a point along this vector that is at a particular relative distance, what we can do is we can try to find which one is the vector AC that we need to add to A in order to get C. And it also follows from this very same relationship that the length or the coordinates of vector AC, which is this one, it follows that it is a simple scalar multiplication of vector AB, which is the longest one, times that relative factor from 0 to 1 or 0.5 or whatever you want. So the vector AC equals this factor times vector AB. So whichever is easier to understand or whichever way of looking at this problem resonates more with you, that's the one that I would like you to stick with. I'm going to implement both systems. I'm going to implement the one on the left because this one is agnostic to whichever geometry library you're using. You don't need vector objects or point objects or anything. And this one is a little easier and faster to do if you are working on an environment that already has points, vectors, or this kind of geometry objects as classes and structs. Like for example, it's the case of Grasshopper, Rhino Common, Unity, or any other geometry savvy environment. So I think we're ready. I think let's get some code cracking. So now, I'm going to implement this algorithm using C# in a C# script here in Grasshopper. So remember, what I have here right now is 2 points that are in Rhino. I brought these 2 points as parameter boxes into Grasshopper. And then, just for the sake of visual flavor, I'm using a line component to just trace this visual line between them. But this line component is actually useless for us because what we care is about understanding a line just as 2 points. Anything other is just visual flavor. So for our component, what we want is, we want the 2 points as inputs. So I'm going to create a C# script component, and then I'm going to right click on each one of the inputs and say this object has to be of the type point3D, this other one has to be of the type point3D, and the value for the normalized value, the parameter along that line, is going to be n, which I'm also going to right click and force this to be a double, so a number with decimal precision. And then the output is going to be the point C. When I double click here, now we can open our C# scripting window, and you can see that we have the main function, which is taking in 2 points, A and B, the parameter, and is returning as a reference the C point object. If you have an environment where you don't have a point object, you can just replace this by x0, y0, z0, and then x1, b1, sorry, y1, c1, whatever. Or you can just create like a small point class, which is super easy to do. Also, I'm going to write this code here as a function in itself, because I will want to use this function and copy paste it between different other components that I may write at some point. Because I'm actually recording this geometry gem because I want to make another geometry gem where I'm going to be using this functionality. So very easy. I'm going to, here, the output of this component is going to be C, is going to be equal to a function that I'm going to call point along line, for example. This is going to be the name of the function, and first point is going to be A, B is going to be the second point, and N is going to be the factor along that. And now I have to actually create that function. So I'm going to create a function that is going to be called point along line, and it's going to take a point 3D object. I'm going to call it lowercase a, another point 3D object, like lowercase b, and a number that I'm going to call the parameter, which is going to be t. And remember, this function will calculate this point and return another point object, which is along this line. So I need to make sure that I return an object of the type point3D. Again, if you are working on an environment that doesn't have point or vector objects, just create yourself like a really quick point class that has like X, Y, Z properties, and it will be super easy to just mimic this functionality. And then once we're here, if we remember, we're going to implement it both ways. We're going to implement it the numerical way first, which is this part here on the left, and then we're going to do the exact same thing with vector algebra, which is only available if your platform, your environment has vector algebra. So what I'm going to do here is I'm going to say, remember from the diagram, the first thing that we need to do is we need to calculate the x, y, and z differences between a and b. And then once we have that, we can multiply them by the factor, so the parameter, and then we can recreate c by adding to the coordinates of a, adding the coordinates of that factor difference. So I'm going to do that very verbosely here. So I'm going to say the coordinate difference between a and b in the x direction is going to be b dot x minus a dot x. So the coordinates, the x coordinates of b minus the x coordinate of a. I'm going to do double dy is going to be equal to b dot x minus a dot, y minus a dot y, and then double dz is going to be equal to b dot c minus a dot c. Wonderful. So so now that we have this, what we need to do is we need to calculate for c how far along those differences it is. So what I'm going to say is, for example, I'm going to say nx, so this distance, how far away in the x direction z is away from x, I'm going to call that nx, and that's going to be equal to t times dx. So if dx was 3 units and t is 0.5, so it's going to be half of that. And I'm going to do that the same, and y is going to be t dot dy. Oh, I'm having keyboard problems these days. Yep, I'm having a lot of these. Is my keyboard working? Yes. So t and double nc is going to be equal to t dot dc. And now that we have this, we can say, let me now calculate the actual coordinates of point C in Euclidean space, so in the world coordinates. And those coordinates are going to be equal to the coordinates of point A plus this difference plus this difference plus the other difference in C that we just calculated. So I'm going to also be very verbose about that. So I'm going to say double cx is going to be equal to a dot x plus nx. Double cy is going to be equal to a dot y plus ny, and then double cc equals a dot c plus nc. So these are the coordinates of point C in world coordinates. So now it's just as easy as saying the point, point 3D C is going to be equal to a new point 3D object that is going to have coordinates cx, cy, and cc. And this function is just going to return that point. Obviously, all this code is a little long and I could have used some shortcuts. So I could just, instead of doing this, I could just like have done that inline here, or I could just have compressed everything as in inline. But for the sake of clarity, because this is an educational video, I just wanted to be very clear about the process. Okay, and then now that we have this, let's see if this runs. Oh, interesting, it does run. So let's see if I now go here and I say, well, let's see if when it goes to 0, we're all the way at the beginning. Yes, we are. And when we go to 1, we're all the way at the end. And anywhere, we're just in the middle. And then if I move these points, so if I now move the point, we can see that the coordinates of that point are adjusting accordingly. So that's pretty much it. That is just as easy as it was. Now, something that I also want to do is I want to do the exact same operation, but with vector algebra, in case you're working in a framework that has geometry objects and you have access to vector algebra, like it is the case here, or for example, with Unity or other such geometry-savvy environments. So what we can do is like all this code, instead of doing it numerically, which is something that will work everywhere because it's just numbers that we were using. What we can do is we can follow the vector approach, in which what we just need to do is we need to find the vector between point A and B. So that's going to be vector AB. Then we're going to do a scalar operation with that vector where we're going to reduce it by the factor that we're looking at. And then we're going to compute C by adding to the coordinates of A, adding the vector C. So it's going to be super easy. So we just need to say, I want a vector 3D object that is we're going to call AB, and that's going to be the coordinates of point B minus the coordinates of point A. And this is something that I can do because here in Rhino script, we can do vector operations with points and with vectors. Now, after that, what I can say is I can calculate vector 3D, I can calculate vector AC by saying this has to be equal to vector AB times that factor. So it's a scalar operation of a vector. So T times the vector AB. And then once we have that, calculating C, point 3D C is just as simple as taking point A and adding vector AC to it. And then if we do that and I run this code, nothing changes because everything is working just the same. And we have this, we can move the point, etc., etc. Which one of these two approaches is better? I'm not sure. I think maybe this one has a little bit more overhead because it has to call functions back and forth. Although this other one is actually, it's creating a lot of what is it called? It's creating a lot of variables in the way. I'm not sure, but they're both very similar. Whichever resonates with you, that's probably the one that you should use, or whichever is available to you depending on the system that you're using. I have point and vector 3D objects here, and I have access to vector algebra in this form, but if you don't, then you probably have to go through this route, okay? Okay, and the last thing I want to show is like some interesting property of this, and it is, the interesting property of this system is that we have talked about how 0 means being at the beginning of the point, 1 being at the end of a point, and then anything between being relative distances. But if I actually open up the range of this slider and I let it move over a larger range, so for example -1 and 2, we can also see that if I go over 1, this is still working because the relative distance doesn't have to be constrained to just the segment. The distance where the point is, even if it's negative or even if it's over 1, is still going to be proportional to the length of the object. So we can see that if we go all the way to 1, the distance between the point and B is 2 times the distance between the point and A. And similarly, if we go to -1, so we also see that this is just an extension and that this distance is the same as this one. So this algorithm can also help you extend a point beyond the boundaries of the line segment. Okay? So this is a very, very foundational algorithm. This function is something that you can probably use for your geometry, computational geometry, toolkit, whatever, because you will perform this operation so often. And actually, we are building this geometry gem because in the next geometry gem, where I'm going to do an algorithm for generating smooth curves out of a polyline of control points, I'm going to be using this operation very, very often. Okay? Before we finish this gem, I would like to show you like a small variation or a small alternative to this algorithm, because we need to keep in mind that what we've done here is we have calculated a point along a line, but we have used relative distance as the measure. So for example, if we have 0.5, this doesn't mean 0.5 units in the world coordinate. What it means is halfway through the length of the whole line segment. So if I move, for example, this point all the way up, or if I move it all the way here, you can see that the calculated point, always stays at the middle, at the center of the line. So that's great, and that's actually much more useful in many applications, in many situations, but we may want, for some reason, we may want to calculate the point along this line. Instead of in relative terms, we may actually want to calculate that point in world coordinates. So for example, if this segment here is 5 units, we may just want to calculate this at 5 units, 2 units away, 7 units away from the starting point, whichever units that might be. So that's actually very easy to do, and I would like to implement that version here real quick. So follow with me. The way we're going to do this is actually super simple, and it goes back to understanding how we did the previous algorithm before. And since we already know how to do it for a relative length, the whole idea here is that it's very easy to go from absolute distance to relative distance, because if we think that that this distance, the distance where we want the point to be, we have it in world coordinates, so in real units as opposed to relative. And if we think that the total line segment is however much long, so we have like the length of the line segment, and we also have the length at which we want our point to be, then it's just so simple as saying, well, if we divide the length at which we want the point divided by the total length of the line, then basically that gives us n, which is the relative length at which that point is along the line. And therefore, now we can go back to the technique that we had before and find where that point is based on its relative length along the line. So by using this formula, the distance where we want the point divided by the total length of the line, that gives us how far along the line this point is, and then we can just go back to the previous. So let's just do that. Yeah, let's do that. All right, so back to the coding board. So what I've done here is I have copy pasted the previous component, that one that used relative length. I've copy pasted it, and I have changed the slider, and I've created a new slider that is that has a bit more range, from 0 to 10, I think. I have changed the name of the input. I've called it lowercase d, just to make sure that we understand the difference between normalized coordinates and Euclidean coordinates, or world units. And then inside of it, I have come here, and I haven't really changed the code. I've only changed here to be d, but this is basically what we had before. Okay. So one thing that I'm going to do now is I'm going to separate the two functions. One is going to be point along line relative, all right? And then so I'm going to change the name here and here. And I run this, everything was well, okay? And I'm going to keep this because what I want now is to create a similar one, a similar function where I say point 3D. I'm going to zoom this here probably for everybody. I'm going to create another function here, and I'm going to call it point along line absolute. And this is going to take a point 3D object, another point 3D object called B, and then a double value. This one I'm going to call it V, so that it's a bit clearer that it's different. But this doesn't have anything to do with the fact that the component is also has a D input. It's totally unrelated. Okay, and this and I'm going to copy paste this. This function returns at an absolute Euclidean distance D between points A and B. And how does this work? Well, it's very simple. The only thing that we need to do is we need to first calculate the length of the line, then we need to calculate n, so how far along the point is, and then we just need to call this function to find that point. So how do we calculate the length of a line segment? Do we have a gem on that? Yes, we did. I just realized we had this gem. So this is exactly what I want to do, and build gems on top of other gems so that we can build more complexity. So if you can go back to geometry gems number 4, and here we did calculate the distance between 2 points, which is the same as calculating the length of a line segment. So I have gone back to the files and I have copied the function. So here, this is the function that we developed in geometry gem. Distance between 2 points, geometry gem number 4. And this takes 1 point, 2 point, and gives me the distance. So what I'm going to do here is I'm going to say double uppercase D is going to be distance between A and B. All right. Now I'm going to calculate n. N is going to be equal to the Euclidean distance that I have as an input in this function, divided by the total length of the line. Okay. Now, as I do that, I can now say, let's find the point 3D P, which is at that relative distance between these 2 points. So I can just copy this and say between A and B, and at the relative distance n. And then that is the point that I return back with this function. So that's going to be return P. All right. And I want you to notice something very nice and very elegant that we have done here. We have a function called point along line relative, and we have one that is absolute. But the absolute one actually relies on the relative one. It just does some pre-processing of the data and then calls the relative one with the normalized coordinate that we have calculated. This is a very common practice, and I find this a very elegant and very nice way of writing code. So I'm going to copy this here, point along line absolute, and then if everything went well, we should see now that this point, if I go to 0.5, it's not at the center anymore. It's like at 0.5 units, world units along the line. If I can increase this, and if I move the point, you're going to see that it's not going to stay at the same relative distance. It's going to stay at the same amount of units along this line. All right? So we have changed now from relative distance along the line to absolute distance along the line in Euclidean coordinates. So thank you for being here, and hope to see you in another video. And if you liked what you saw, please subscribe, hit I like, turn on notifications, and all that stuff. You know how it works. Thank you.